SETI, and he will be talking about SETI and possibly its relation to astrobiology as well. So if you have any questions, please feel free to ask him any questions, anything that you don't understand. He's a very casual and a very friendly person, so feel free to ask your questions and concerns. And to Vishal, we will start the session, and we do have a meeting that we might have to attend. So we will be on and off, but we'll be there here as well. So just letting you know in case we're not there immediately. All right. Okay.
No worries.
Yes. Masood, are you there?
Yes, ma'am.
Yes. Can you make all the student panelists as well?
Yes, ma'am.
Yes.
Okay, ma'am.
Thank you. Okay, Vishal, the floor is all yours.
All right.
Oh shit, मैंने unmute कर दिया.
Okay. I'll let a minute or like a few seconds for all the students to join.
Yeah, sure.
Or if is everybody here, then I can start. Looks like 1, 2, 3, 4, 5, 6, 7. I guess yeah, we have. Looks like there are 7, 8 people. Yeah.
Yes, everybody's here.
Okay, excellent. Well, first of all, thank you so much, you guys, for giving me this opportunity to talk to you all about the work that we do here at UC Berkeley, as well as at other places across the world, including at MIT University, in fact. So I will briefly touch upon what we are doing at MIT, along with our current global effort. But the entire topic of today's talk will be searching for extraterrestrial intelligence. Like, what are the current state of the field is? I mean, I tried just to kind of give you an outline. My entire talk, or sort of this lecture today, will be divided into these 4 sections. These are like fairly broad. We will first start with the justification of why we think that the search is important, and then I'll talk about what are the ways by which we are currently doing the search, what are the challenges we face, and what is the progress we made so far. All right, so let's jump right into it. So the first question is that I guess all of you have wondered about this when you have looked at the night sky, right? When you see thousands of stars, you have wondered that are we really alone in the universe? Like, because these are all stars, so just like our sun, and we know that these stars can have planets. So definitely the question comes: are we alone in the universe? Is Earth a unique place where life is the only place where life has sort of got an opportunity to arise and evolve? So far, the evidence are sort of coming in our favor that we are most likely not alone. Why am I saying that? The first evidence, which I feel are quite important, is the number of exoplanets that we have discovered so far. So these are the planets that are not associated with our sun, but these are extrasolar planets, the planet that we have found around other stars. And there are several thousands of them. And we have found, in fact, several Earth-sized planet inside what we call an habitable zone, where water can remain in a liquid form, which is quite essential for life to arise and evolve. And hence, there are potential places that are kind of now, we can just kind of speculate now, because there are probably more number of planets in our Milky Way galaxy than the number of stars. So there is a huge amount of real estate out there, and it's unlikely there's only one occupant on all of it. So the picture is kind of changed now. Like earlier, when we used to look at the night sky, we used to think they are all just blank, just sort of point sources, just stars. But what we now can say with confidence is that there are almost all the stars that we see in the night sky will probably have planets around it. The second piece of evidence comes from what you guys work on, is through astrobiology. People have found a number of evidence on our planet itself about extreme forms of life. You have discovered life at places where we don't really expect them to be there. Things, for example, like at the bottom of the ocean where there is no sunlight, where the pressures are just extremely high, people have found life. Even in space, like you all probably know about water bears. I don't really need to kind of explain this to you guys, but like these are really good cases. This means that the life, if one starts, can basically survive. And that's what the kind of is another motivation for us, that the evolution of life, like once life gets started, even though there has been like a number of mass extinction event on our planet itself, life has survived. So life finds a way, even if there are natural obstacles, it finds a way to kind of cross that. So it is very likely that even within our neighborhood, even within like a few, like close to us, there must be a life. So how do we find it? So that area of research is called biosignature, where we actively search for molecules which are tentative signs of life on the surface of an exoplanet. So this is a technique which is called the transit spectroscopy, in which when a planet passes in front of a star, the light of the star actually goes through the planet's atmosphere. And you can take a spectra, like using the JWST, which now I guess all of you are probably have heard about. Powerful telescope like JWST can actually take spectra, and we can search for biosignatures. And there are, in fact, some tentative evidence people have found about potential biomarkers in our, there is a system called K218b, where they've in fact found some interesting cases. So this is all very exciting. This means that even like within our and that system is like just 100 light year from us, you know. So all this means is that even within our neighborhood, there are potential places where life might have already begun. That's already there. Um, we haven't really found a concrete evidence, but if the life has probably started in any of the other places, it will also probably evolve, and then it becomes advanced and intelligent. So the question comes, how do we find advanced and intelligent life? Our biosignatures may able to discover life, but obviously those evidence will likely not be something that we will be sure about for many, many years. It will take huge amount of effort. But if you find evidence of intelligent life, you find evidence of sort of extraterrestrial intelligence, that will be a sure sign that yes, life, we are not alone in the universe. And that's why the entire effort, I think, that puts more focus on this particular question, that are we only intelligent species in the galaxy, or there are more intelligent life? So with all this, I think now, hopefully I was able to justify that why we all feel that life on our planet is not so unique. It's probably just a natural process. It's just the base chemistry, and it probably must have started in other places as well. So it's out there. Now the question is, how do we find it? How do we find intelligent life? So there are a number of ways by which people have suggested that one can find and look for intelligent life. You can think of the way we are progressing right now. If we continue the same route about our technological advancement, we will ultimately be able to be an intelligent or advanced species, where we will need the actual energy requirement of our planet will be so much that there won't be that much power will not be available to us sitting on Earth. And we run out of all the energy that is necessary to run everything that we are doing. And hence we have to look at our nearest source of energy, which is the sun. And then we might try to capture all the energy of the sun itself. And this hypothesis is what we call the Dyson sphere. So an extremely advanced species might build some kind of an enclosure around their parent star. And these Dyson sphere can be detected across large interstellar distances. For example, here is an example of what we call a light curve. So when you look at a particular star, you look at the light coming from the star as a function of time, and you see that at some time the light sort of disappears. There are these dips, and these dips are quite irregular. Only in one system they have found it. These irregular dips may mean that this particular system might have some kind of a mega structure around it. Although later on it was ruled out to be that this is more likely to be some kind of a gas cloud. but it's an interesting kind of a hypothesis to test. The other way is that for example, we have launched some of these space probes to explore our own solar system, and they are also traveling, and they, in fact, they left our solar system, these Voyager's probe, right? And we have left signs on these probes about where Earth is located. I mean, one doesn't really need to really point that, or just one can even just look at this object and say this is not a natural object, and even finding something like that will be a sure sign that yes, it is built by an intelligent species, and hence we are not alone in the universe. But the problem is that we cannot travel faster. So these kind of probes, like for example, are produced by extraterrestrial intelligence, probably may never reach us, and we may never really see them. So not a likely way or the best way by which we can rely to find life. So what are the other ways? So the most, I think, in my opinion, the most efficient way is detecting an electromagnetic waves is the best way by which we can identify if life exists out there or not. Now, for those of you who are not from I'm sure all of you are familiar with it, but just to give you a recap on what electromagnetic waves are. So electromagnetic waves are of different varieties based on their frequency. So electromagnetic waves of the lowest frequency are what we call the radio waves, while the electromagnetic waves of the highest frequencies are what we call the gamma rays. They are all part of the same they're all electromagnetic waves, gamma rays as well as radio waves. The only difference between them is that their frequency are different. So electromagnetic waves also includes optical, like the light that you see me right now, that is also electromagnetic waves. Our atmosphere, fortunately or unfortunately, allows only portion of the electromagnetic waves to reach to the ground. Now, why do I say fortunately? Because that's a good thing, because it actually stops some of these high energy electromagnetic waves, like from gamma rays and X-rays, to reach Earth's surface. If it does not allow that, then what will happen is that can destroy life on the planet. And so it's a good thing that we don't really get a lot of X-rays and gamma rays from, for example, the sun produces a huge amount of them to reach us. So, but there are two windows. One is in radio, second is in optical. So at these two windows, we can see the universe. So we can study the universe by using light. So I guess all of you have seen the stars or interesting astronomical sources like Saturn or Moon through a telescope like we did, right? Similarly, we can also detect radio waves and study the universe. And this entire area of research is called radio astronomy. So this is a radio telescope. A radio telescope is different than what you might have thought about what a telescope will look like. So as you see, this is what I guess you might think a telescope would look like, but in fact, all of you are carrying a radio telescope in your pocket. Like all mobile phones have antennas inside them, and they are, in fact, they are telescopes. The only difference is that the telescope we built are massive in size. They are not tiny, and because the kind of signal we try to detect are extremely weak. So why am I saying that radio waves are? So my entire rest of the talk will be focused on searching for evidence of intelligent life using radio waves. There are a couple of reasons why I feel like the radio waves are best way by which you can communicate across large distances. Number one is that they are energetically extremely cheap to produce. So we produce them quite a lot. For example, this is the Arecibo telescope. Unfortunately, it's no longer active. It was sort of ran out of its life and decommissioned, and I think it broke off. But when it was operating, it used to transmit these powerful radio waves to detect asteroids or detect objects in our solar system. Now, these objects are important to be detected to sort of protect ourselves. But the radio waves that we produce no longer just kind of stops at these objects. They also continue to travel in space. So what you see at the bottom plot here, this is, for example, if the Earth is here, the radio waves that for example, the Arecibo had produced to detect these asteroids are so powerful that you can detect them at all the way to the other end of the galaxy. So these are the advantage of radio waves, because we already have the technology. We already have the necessary tools to produce such a powerful radio waves that can be detected across large interstellar distances. And hence, it's likely that radio waves are likely to be the best way by which you can communicate across large distances. The second kind of radio waves are the radio waves that we leak out by our own communication. Like this is where I'm currently located in the Bay Area in San Francisco, and we have the Sutro Tower right near San Francisco Hills, which is like a warning signal. It produces some kind of warning messages in case of some emergency. But it also produces powerful transmission that can be detected at least up to a few light years away. Moreover, there are these planetary, as I said, radar signals that are being produced. There are aircraft radar signals that can be produced. In fact, there was a study done by one of the students who is working with us, Miro Saeed, who actually looked at all the different mobile phone towers that are currently in operation and looked at the collective transmission that is currently leaking from the Earth, from all of these mobile phone towers, and it's quite high. In fact, it is of the power of 10 to the power 10, 10 to the power 10 volts, so like at the level of like gigawatts. So these are like extremely powerful signal. Although the individual station, individual sort of tower that is transmitting, mobile phone tower, is not so bright. But when you collectively add all of them together, they can reach extremely high level, and hence they can be detected. So this is an example that he's showing. That the map here shows every red dot is a mobile phone tower, and as the Earth rotates, like for example, you take a distant star, and imagine that there are extraterrestrial intelligence who are looking towards the Earth, and as the Earth is rotating, different part of the world is pointing towards that particular direction in the sky, and hence you see the power levels are changing. Like for example, when India faces the direction towards that star, you see a bright emission coming from the Earth. And because India has a lot more number of mobile phone towers, and similarly, like when China faces, you see a huge number of sort of pick in the power level. But the idea is that there are huge power that we are already leaking. So now the question comes, okay, great. There are radio waves that we are already producing, which are so powerful that we can detect them across interstellar distances. What is the likelihood of finding it in our neighborhood? So that I can tell you, because we don't know, frankly speaking. We use this formula, which you might have heard, called the Drake equation, in order to roughly estimate that what would be the expected number of such civilizations will be out there, which can communicate with us. Frankly speaking, we don't know the individual parameters. We only know up to, let's say, so I'll not have time to go into the detail about each and every one, but you can think of it as like a probability distribution. Like each term represents what is a fraction of, like, for example, stars will have planets, what fractions will have Earth-like planet, what fractions will have life on them, what fraction of those will probably have an evolved life. And those evolved life will develop technologically advanced or will be technologically advanced enough for us to detect. So we don't know these numbers, frankly, right? So we can take two approaches. One is that we can take an extremely pessimistic approach, in which case we can assume that almost every planet that is in our sort of in a galaxy will probably evolve to evolve advanced life. Or we can take an extremely pessimistic approach, in which we say, oh, the likelihood of is less than 1%. So if you take these two end goal, like pessimistic and optimistic, you end up with two different numbers. Now, pessimistic value is something like are slightly discouraging, which means that there are probably one intelligent life per 100 galaxies. Not every galaxy will have life on it. Maybe we are an extremely rare case. Or if you take a more optimistic value, then maybe there are millions of such stars where you have one life per million star. So there are millions of them. So basically, there are thousands of them in our Milky Way galaxy. So these are both two extreme cases. Again, this is a theory. We don't know. So what is the best way to do it? And I would like to quote Carl Sagan here. The only significant test of existence of extraterrestrial intelligence is an experimental one. Unless and until we conduct experiment, we cannot really distinguish between what is the reality, whether it's a pessimistic value, whether it's an optimistic value. And with that goal in mind, Breakthrough Listen was launched in 2015 at the Royal Society with late Stephen Hawking was one of our founder of the program. Unfortunately, he's no longer with us. Professor Martin Rees is also one of the primary founder who initiated the entire project, and he still sort of act as our advisor, and we basically work with Martin Rees, and we get a nice advice from him once a year. So Breakthrough Listen's entire goal is to search for evidence of intelligent life. Recently, it used to be operated entirely at Berkeley, but now we have decided to shift our headquarters from Berkeley to Oxford. So all of us who are working here in Berkeley will probably have affiliation with Oxford as well. This is largely due to the upcoming telescope that's coming online called the Square Kilometer Array. But the goal is still the same. We are all going after one goal of searching for intelligent life in the universe. So you may ask, like, what are the different things that we are doing? So I'll again go back to the original pessimistic and sort of optimistic values. Like if you assume a pessimistic scenario, maybe there's one intelligent life per 100 galaxies, or an optimistic scenario where there is one intelligent life per 1,000,000 stars. So taking both of this into consideration, what should we do? We should do both. We should search all our nearby stars, and we should also search our nearby galaxies. I think that's a logical thing to do, and that's what we are doing. We are searching our entire solar neighborhood. So our goal is to search every star within a certain distance to us, and that's at close to like 1,000,000 stars. We are also searching extragalactic sources like the nearby galaxies, because you never know. You don't know what is the likelihood of life to arise, and maybe it's rare. Then maybe they are there at the other in any of the other galaxies. Although the likelihood of detecting a powerful transmitter from galaxies that are like several millions or several hundreds of million light years away is probably less, but you can imagine an extremely advanced civilization to produce extremely powerful beacon. So we don't know that, but we shouldn't. That's why we should not stop just looking at our neighborhood. We should also look at the nearby galaxy. So our survey consists of number of nearby stars, as well as we are looking blindly in the entire plane of the Milky Way. Like when you go, especially if you have access to dark skies, if you go at night, you might see that's why we call Milky Way, right? You see the blue sort of stripe in the sky, which is our galaxy. So we are searching the entire galaxy, the entire plane. And we are looking at the nearby galaxies as well. Like the most important part is that the amount of data we collect is equivalent to a year of data that has been collected by previous searches. So this is definitely a huge step function, right? Whatever was happening before we started operating was probably just small. It's extremely small compared to what we are doing. So because that's why we say that a day of Breakthrough Listen is equivalent to a year of previous search, because that's the amount of data that we usually collect. So just to recap of the entire idea, let me give you a sort of nice little animation, which nicely describes the entire idea that I was talking about. So the idea is that we are living inside this Milky Way galaxy. Potentially it is habitable, and then there are a lot of places where life has arisen and basically are broadcasting these signals. And you see these bubbles there, you can think of them as like radio transmitting bubbles. So let's take an example of a planet which has life on it. It developed intelligent, it developed technology, and then it started producing radio signals. Now, due to some reason or the other, life on that planet perished. It no longer exists there. And that's why it destroyed, and the radio signal itself stopped broadcasting. But that radio signal, even if it broadcasted for a little bit, is still traveling. and is still reaching to other parts of the Milky Way. And we here sitting on Earth, we ourselves are producing radio waves, but at any time, these radio waves that are produced by an intelligent life, which may not exist right now, but these radio signals that are produced from them can still exist, and they can pass through it. And we use powerful antennas like these. This is the Green Bank Telescope in West Virginia to detect these radio signals. There's another telescope that we also use quite often is the Parkes telescope in Australia. So these are two of the powerful telescopes that we use in order to search for the radio signal. Not just that. So this is why I feel very excited about the Breakthrough Laser program, is that we have access to not just these two telescopes, the Green Bank telescope and the Parkes telescope. We have access to all these other radio telescopes as well, where we actively conduct searches. This is a telescope that all of you are probably might be familiar with. Is GMRT in India. This is where I did my PhD, which is quite close to Mumbai, near Pune. And if I want to give you a scale of frequencies across which we are searching, these are the different ranges of frequency. So all of you are familiar with the FM band, right? When you tune your radio, it goes from like 88 to like 108 megahertz. So these are again radio frequencies, but they are called FM band. So you can go in radio frequencies to as low as like 30 megahertz or 10 megahertz. Below that, the Earth's atmosphere again doesn't allow radio waves to kind of penetrate. So there is a range to start with, where our radio window starts somewhere around 10 megahertz. So we are searching close to that from 30 megahertz. So as you can see here, this is a range of frequency, and these are number of radio telescopes that are currently being used, starting from 30 megahertz all the way to 100 gigahertz. And then we also use a couple of other optical telescopes. As I said, the second window that's open to us is the optical window. So we are also searching for electromagnetic waves in optical domain as well. And there are these two other telescopes that we actively kind of use for that. Just to give you an idea about a typical radio telescope that we use quite often, this is the Green Bank telescope, as I mentioned. It's world's largest steerable radio telescope. In fact, it's the second largest movable structure. The number one was the enclosure they built for the Chernobyl disaster. So they basically built an entire enclosure, which they only moved once to cover the power plant that was destroyed. This is a 24/7 movable structure. So it's massive in size. You can see the scale of human, kind of somebody standing, and you can see the size of like a car that is parked right next to it. So it's a massive, massive antenna. So we use that telescope almost 20% of the time to search for evidence of radio signals. So that covers how, I guess, right? So we started with why we feel that the extraterrestrial intelligence are probably there. We covered how we can find them. We talked about a couple of ways by which you can find them, like you can search for their mega structures, you can search for electromagnetic waves, and we use number of radio telescopes in order to search them. But then what are the challenges? Like, what exactly are we searching? I mean, let's go a little bit more into the details, and then we try and understand the process, because that may sort of let you appreciate the amount of effort that goes into searching. This is not just a simple task that you just point a telescope towards a star and just listen like a headphones, like in the movie Contact, right? It is not that simple. It's heavily complicated. So I try and kind of give you a little bit of an outline of what exactly we are doing. So what are the challenges about searching for the signal? Now, the rest of this is divided into two parts, like what are the type of signal we search and what is the interferences that we get usually from these signals. So very briefly, we search for whole different kinds of signals. The number one kind of signal we search is this called narrowband signal. So what you're seeing in this plot, frequency is shown in the x-axis, the power is shown in the y-axis, and you can see a peak in power here. So what this means is that this is a signal that is concentrated all its energy into just few hertz. Now you may ask, why is this important? So far, in all the natural sources that we have studied, we have never come across a source that produces a narrowband signal, but we produce them quite a lot because these are the evidence of technology. This can be produced very easily by instrument, by technology that we have developed. So if you detect a signal that is extremely narrow in frequency, that's a very good sign that it is produced by technology. So these are the kind of signal that we search. We also search for signals that are modulating. We have never come across a signal in nature that has such a modulating pattern that may carry information, right? We produce them quite a lot, like all the mobile phones, for example, are producing modulating signal, and that's how they're talking to their uh, telephone towers. So these modulating signals are also quite useful, and we search for them. We also search for signals that are extremely broadband, signal that kind of spans several gigahertz, and they show properties that we cannot expect them to show because we have seen all the natural sources, how they behave across large frequencies. But if you see the same, if you see a source which is behaving differently than what we expect it to do, that is again a way by which you can search. So this is just a sort of example. This is no way a complete set, but this is just to give you an idea about what are the exact things we are searching. So, I mean, I already explained the narrowband signal, but tell you a little bit more about how we do it. Is that we basically take the data, which may look like this, is some just random noise. But when you take a Fourier transform of the data, you can break the signal into multiple frequencies, and that's how you detect if there are any narrowband signals in them. But the major challenge with searching for any of these class of signal is the radio frequency interference, or in short, what we call RFI. So radio frequency interference are the interferences that are produced by our own technology. So we use radio waves for our own purpose, right? And that causes a huge issue to us. Like, how are we going to search for signal which are similar to what we are producing? Like, for example, this is an example of a radio telescope. Unfortunately, radio telescopes are, although they are great at detecting extremely weak signal, that is again a drawback, because if there is a transmitter that is close to the radio telescope, just by the sheer size of it, it is extremely sensitive. It can still detect something that is at close to it. Even if it is not pointing towards there, even if the telescope is looking towards the sky, in that part of the sky, it still has some sensitivity to everywhere else. So even if there is any transmitter that is nearby, it will still pick it up. And that's what we call the radio frequency interference, and that kind of always seeps into our data, and we have to get rid of it. The second challenge is satellites. Our sky is full of satellites. Like, this is just an example of like a satellite that are currently there in particular directions that we are observing. There are satellites that are in geostationary orbit, which are fixed. There are satellites which are in the low Earth orbit that are just moving past all the time. So yeah, these are challenges. Like, how do we reject things that are produced by our own technology? And we try. So the next few slides, I try and give you an outline about what are the different ways by which we can eliminate these different sources of interference. So one of the standard way by which we try and eliminate sources of interferences is by staring the telescope on and off the source. So what do I mean by that? So what I'm showing you here, this is a telescope I mentioned earlier, the Green Bank telescope. It is looking towards a star. And what you see here in the green color is, you can think about is like some kind of a beam. Like, this is the beam that where it is trying to receive the signal from that particular star. What you're seeing on the right-hand side is the frequency shown in the x-axis, and time is shown in the y-axis. And you can see that there is a tentative signal. This is a narrowband signal that I mentioned earlier that is there when you're looking at the star. Now, how do I verify it is coming only from the star and not from somewhere nearby? The way to do it is that I look away. I point my telescope away from the source. If the signal disappears, that means that it is actually coming from the source. Why is that? Because all the sources of interferences are always there, no matter where you look. So if you look at a star, or if you look at your source of interest, or you look somewhere else, the interferences are always coming in. So if you look at a different part of the sky and you see the same signal, that means it's interference. So you can do this multiple times. So we do this like 3 times. We do on, off, on, off, on, off. And if the signal of interest is persistent on one particular part of the sky, that is a sure sign that it is coming from the source. It's not coming from an interferences, and hence this way you can eliminate local sources of interference. The other way by which we try and eliminate is by using multiple beams. So this is a telescope, as I mentioned earlier, the Parkes telescope in Australia. It no longer has this, but when we were using it, it can look at 13 different parts of the sky at the same time. Like the Green Bank telescope that I mentioned earlier was looking at one part of the sky in that example, but the Parkes telescope can look at 13 different parts of the sky. So we can point a telescope towards the star of our interest and compare the signal coming from all the 13 beams. If the signal is only there in that particular beam, like here, what you're showing, what you see is that this is the sky, this is our star, and these are the different beams that we have projected on the sky. These are the different points in the sky from which we are collecting the signal, where our source is located there. So if you see a signal only coming from, let's say this is beam number 12, that's an interesting case. And if it's not, if that signal is not present in any of the other beams, that way you can eliminate that it is coming from source or whether it's interference. The third technique is by using telescopes that are spread far away from each other. So these are the telescope, for example, that we use called LOFAR, and we simultaneously use multiple telescopes at the same time. So these two telescopes are actually located, one is in Ireland and second is in Sweden. So they have roughly around 1,000-kilometer distance between them. And both of these telescopes are actually looking at the same part of the sky. So if you see an interference, like for example, if you have a mobile phone that is next to one of the telescope, it's likely not going to, it's definitely not going to interfere with the other telescope. And hence, if you compare the signal that you detected from both the telescope, you can eliminate what is sort of local to the sources versus what is actually coming from the sky. So that's technique number 3. Technique number 4 is by using interferometer. So you can use a radio telescope in multiple ways. It is impossible to build bigger and bigger dishes because it's a huge engineering challenge, but you can simulate big dish by building lots and lots of smaller dishes. And this is what we call radio interferometer, where this is a radio telescope as well, but it is not like the dish that I showed earlier, but it is actually many, 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 many small dishes. And we combine the signal from all of these dishes together, and then we can digitally look at different part of the sky. This is called a multi-beam search. In fact, so this is where the Amity student that we were working earlier last year played a significant role. So these 4 students who were working as a junior research fellow at Amity University, they developed this pipeline of searching for these signals using the giant wave meter wave. This is the giant meter wave radio telescope in Pune, in India, which we are actively using right now. So they contributed they made a really good contribution to search for these ETI signals using interferometer. But that is still not enough. So this is method number 4 I mentioned. It's still not enough. We still get interference even if we try and use all of these tricks. The other ways which we are trying to kind of now utilize is using machine learning. So we use ML to try and identify signals that we have already seen before. So you can use ML in 2 different ways. You can train a machine to classify things that is already known to us. Like you might have already heard about what they call convolution neural networks. Like for example, like self-driving cars are heavily trained on CNN. They can basically detect objects which are trained, which it is basically trained on that, okay, these are the object. I guess now the technology has evolved. This is slightly older slide maybe. People are no longer using this. They may be using some anomaly detection, but the idea is that you can use a known classes of signal. And then, for example, like the example that I showed you earlier, since we know exactly what we are searching for, you can train a neural network to search for these kind of signal. So like these 3 examples that I showed you, like the broadband signal, modulating signal, or the narrowband signal, you can basically simulate these signals, train a neural network, and then search for these signals. The other signals, or the other type way which we can use artificial intelligence, is look for anomalies, look for things that are sort of completely anomalous, things we don't really expect to find. And for that, we use this thing called LSTM, or long short-term memory network. This is something that people use in speech prediction, like when somebody is sort of forming a sentence, you can always predict what would be the next word with a certain probability. So in the same way, the way we can do is that based on the amount of data we have collected, we can predict what would be the expected outcome. If you don't see that, we call that an anomaly. This may still not be enough. We will still get a lot of interferences. We may still not be able to reject it. The other way which we are currently thinking is actually just abandoning the search from Earth and going to the moon. The advantage of doing this is because, as you know, moon actually only faces one of its side to us. And the other side is what we call the dark side of the moon, is always facing the other way. So if you put a radio telescope on the far side of the moon, you can effectively eliminate all the sources of interference that are produced from Earth itself. Moon acts as a shield. So Breakthrough Listen program is also actively engaging, and we are currently exploring options by which we can launch a mission by which we can install a radio telescope on the far side of the moon in order to eliminate these sources of interferences. Okay, so I hope that I was able to give you some flavor of the different kinds of signal research and what are the ways in which these signals can get interferences, what are the ways by which we eliminate these interferences. So just now I would like to wrap it up with a couple of 2 or more slides. What is the progress we made so far? Okay, we've been searching for last a decade or so. Have we found anything interesting? We have found some interesting cases. We detected an extremely narrowband signal, which was published in Nature. We used some clever machine learning algorithm, and we detected some narrowband signal that were missed before. But in almost all of these cases, we were able to explain them using that. When we actually looked at a little bit more deeply, a little bit more carefully, we were able to eliminate them. We came quite close when we were using this telescope in China called the FAST telescope. Again, this is a 19-beam telescope. So I mentioned about the PARCH telescope, which was looking at 13 different parts of the sky. The FAST telescope can look at 19 different parts of the sky. So what you're seeing here is same frequency versus time, what we call a waterfall, and each panel represents signal from one of the 19 beam. And you can see something faint in the middle beam here, right? Like you can see a vertical line. So when we saw this signal, we got all very excited because this is exactly what we are searching. Signal is only present in this one particular beam. It's not present in any of the other beam. You can see that. You can try and kind of zoom in or squint your eyes or try any different ways, or you can try different statistical techniques in order to detect extreme, even if they are there. We couldn't find it. So yes, that was great. We said, okay, yeah, did we find ET? But unfortunately not. We noticed that the signal was highly polarized, and it was only present in one of the two polarization, which is typically not the case for any astronomical source, because the astronomical source, when the signal passes and reaches to us, it probably distributed signal across multiple polarizations. So you don't expect the signal to be heavily prominent in one polarization and not in the other. This is a typical sign of interference produced by our own technology, and hence this was kind of ruled out. But this was a very interesting case. All right, so to give you a little bit of our idea about everything collectively, what we can say, I'm trying to show you a collective thing in this one particular plot. So bear with me what exactly I'm trying to say. The x-axis here represents the output power of the transmitter. The y-axis here is representing transmitter rate. So what are these numbers? So output power. So you can think about it that way that I mentioned earlier, right? That if you collectively look at all the mobile phone tower transmission, they are at the level of gigawatts. So this is in log scale. So gigawatt is sitting somewhere in this corner. The scale starts at 10 to the power 10 volts. It goes all the way up to 10 to the power 24 volts. So that's just to give you a scale of what are the typical output power that we are sensitive to. The transmitter rate, on the other hand, is the number of transmitter per star, right? So let's say every star has a transmitter on it. Then every star, that means that the transmitter per star is 1. So it's somewhere here. That means it's log. This is again in log scale, so it's 0. But let's say that there is 1 transmitter per million star, so 10 to the power. So 1 transmitter divided by 10 to the power 6. So 10 to the power minus, this is in log scale. So 10 to the power minus 6 is here. So you, let's say as a SETI astronomer, you conduct a survey, and let's say you say that, okay, I did a survey of 1,000 star and I did not find any signal. What does that mean? It means, and one question that I might ask you is that what was your sensitivity? So you can say, okay, I was able to detect 10 to the power 12 volts of transmitter. This is still not what we are talking about in the mobile phones, but it is close to that. So we are searching, so we were able to eliminate anything that is powerful more than 10 to the power 12. So if the signal exists, they probably exist in this direction. And since we searched 1,000 stars, so the number of transmitter is less than 1 in 1,000 star with that transmitter power. So the number of transmitter rate is probably lower. So if you look at everything we did, all of the different surveys that we have done over the year, this is the limit that we can put. And we can reject this parameter space. What does that mean? That there are less than like a few thousand transmitter with extremely high power transmit. But there are also, if you look at the extremely bright ones, like 10 to the power 12 volts, they are probably even more rare because we have searched for them and we haven't found it. So if ETI exists, it probably exists in this region. So what does that mean? It means that in future, we need to carry out searches for extremely weak signal of the level of, as I said, gigawatts, which is what we are transmitting. So we need some surveys that can go to this particular direction, and we need to look at many, many stars. And hence, if the ETI is hiding there, we should be able to catch it. So I compared that to what we historically have done for gravitational waves. So for people who are not familiar with this, gravitational waves is another way by which information can travel through interstellar distances. These are not electromagnetic waves. These are the ripples of space, sort of how the space is expanding and contracting due to the motion of massive objects. These are called gravity waves, and we have detected them, but they did not come that easy. We were searching for them for 50 years. So what you're seeing here, although it's quite complicated, what I mean to just show you is that each line, as you see, as it goes from top to bottom, these are different surveys that people continue to improve their instrument, and eventually they were able to detect it. So it is something similar to what we do in field of our research as well, that although we haven't found anything yet, but I suspect that as we kind of improve in our technology, we conduct more and more sensitive searches, we will be able to push the limit, and then ETA will have no way to escape and we'll find it. So I'll just end the presentation with this final slide that are we alone in the universe? So we are actually in this new era. We don't know. And we hope that we are probably not alone. The idea is that because we have so many exoplanets, the astrobiology is also indicating that the life can survive in extreme environment, and hence what we should be doing is searching for it. So I invite you all to join us if you are interested to learn more. Go to the first slide. My email address is here, and also along with my website. So if you want to find out more about my research, you can go to my website, or if you have any more questions, feel free to reach out to me. And with that, I'd like to take questions. So thank you so much for your attention. So should I take question? Should I take question from the chat, or people can just ask me, and I can also kind of answer
Yes.
here directly.
I actually encourage the students to unmute themselves so that they can actually ask the questions if they feel comfortable enough, or if they better with the chat, that's fine as well. To the students here, please note that this is a part of your introduction. So please engage yourself as much as you can if you have any specific questions. I can through chat, Vishal, if you like.
Sure. Let me start with a chat question, then we can start the discussion. So I think the Pallavi Das is asking that based on the range of the electromagnetic waves, do we suspect that there will be other spectrum that we haven't really discovered where we should be searching? So far, Pallavi, I think when you talk about the electromagnetic waves, we also associate energy with the electromagnetic waves, right? We can divide the electromagnetic waves into, as you know, extremely high frequency electromagnetic waves are called photons. So photons have certain energies. So when we talk about gamma rays will have certain energy, and we have detected gamma rays that are like so powerful that if you collectively look at all the stars in the universe, the output power of all the stars, we have detected gamma rays that are even powerful than that. So you can think about that way, that if we have already seen the part of the electromagnetic spectrum that is sort of so far out, but these are still gamma rays. We don't suspect anything that is kind of beyond that, or whether we can define it something else. These are called, you can maybe specify it as an extremely high energetic gamma rays, but they are all part of the same electromagnetic spectrum. At the lower end, we don't know. I mean, if there are extremely weak electromagnetic waves that is extremely low energy, then yes, I mean, we do use radio waves at kilohertz that bounces off on our upper atmosphere, the ionosphere. Yes, there are radio waves that are extremely low frequencies, but yes, we can still detect them, although they cannot penetrate our atmosphere. So they were limited from sitting on the ground. So we may need to go to space in order to detect them. But yes, we know about them as well. So I hope that kind of answers your question.
Yes, sir. Thank you very much.
Okay. The next question is from Renish. Since light bends near large objects like stars, is it possible that the radio waves we send are also affected by this effect?
Yes. So radio waves are not different from light. So whatever happens to light happens to radio wave as well. So if the radio waves are passing near a massive object, they will certainly get bent, and you will see that effect. So in fact, people have, this is very interesting, because what people have done is that they've looked at a cluster of galaxies, which are massive, right? And they've looked at a bright radio source behind it. So what happens is that this bright radio source, when it is behind this cluster of massive galaxy, the light from, or the radio waves from this bright radio object actually gets bent and comes around. So you see multiple images of the same source. So yes, it does happen, and people have seen it. Yes.
Okay. I just have a question about you talked about the dark side of the moon, which was interesting, and I may have missed it. Do you think that's a option in the future to use, that to help with this process?
Yes, so I think we are in an active research in this topic. It is still challenging to launch a massive amount of sort of project to actually install a radio telescope on the far side of the moon, but we are in the design phase. So what we are doing right now is we are currently understanding the technology requirement for such a mission, the budget that such a mission will carry. And then we are also soliciting potential partners, different space industries who can basically do this for us cheaply. So there are a couple of private ventures who have basically expressed interest. Australia is playing a huge role in facilitating this, as well as India might be able to play a huge role in enabling it. But so yes, if we are able to find a cheap and effective way of launching, even like a small scale telescope may not be as big as, like, you cannot have like a green bank size telescope on the far side of the moon. It's just impossible. But even like a small scale telescope, if we are able to kind of install, that will still be a huge step forward.
Okay, so just kind of a follow-up, and maybe this is not exactly related to SETI, but do you feel like any of the upcoming missions, whether it's India or JAXA, could contribute to the initial steps of something in this process,
Yeah,
or
so
it's just too early to?
no, so in fact, it has already happened. So the Chinese mission, I forgot the name, already carried a radio antenna on board. And they demonstrated that, yes, it is indeed the radio frequency. I don't have that image here with me, but they actually broadcasted back the radio spectrum it was limited, but that was extremely clean, which is what we would expected, that it is the far side of the moon. So you'd expect extremely clean radio spectrum. And this is what we also got. So yes, it has been demonstrated already by or some existing mission. And yeah, I'm sure other future missions can be utilized. Somebody can piggyback on having a small scale radio telescope installed as a part of it, and then maybe can study the radio spectrum through it. Yes.
Okay. All right. Thank you. There's one question from Lazi. Currently, there are research going on for the search of the extraterrestrial intelligence, but what are the goals? What are we going to do with that information apart from looking for a habitat? Maybe the big picture after SETI.
I guess I can say that for us human, this will be the biggest discovery we have ever made for humanity itself. Like, this is the biggest question we have been asking science for millennia. We have not yet kind of found answer to that. Like, because even our ancestors who used to live in cave, they used to look at the sky and they used to wonder about the same thing, and they made up different stories about it, right? So, but now if we ever able to kind of come up with a sort of conclusive evidence that yes, indeed, this signal that we have detected is coming from an extraterrestrial intelligence, that will be the biggest discovery on itself. Now, the second part is whether we will be able to do anything with that is a question for the future. We don't know whether we will ever be able to extract any information from it. Is the signal, if the signal is carrying an information with it, whether we will have a technology to even decipher it or understand what that means. It's a question for linguists and mathematicians to figure it out. But for us, even just making a detection itself would be a huge discovery. And I mean, to answer you in a different way, that again suggests that physics or mathematics or the laws of nature is universally true across everywhere. So that's a good way of understanding the universe.
Right. Okay. There are any more questions, you can always contact Dr. Vishal. I can share his email ID with the students as well. So if they have any follow-up questions specific that they think about later on, feel free to contact Dr. Vishal. And of course, I'd like to thank Dr. Taking time for this talk. I'm sure and I hope the students very useful, because this is something that we are going to quiz them on a little bit later on. So I really hope that it was. And thank you so much for providing background and, for connecting this. So we appreciate the guidance. And of course, to the students, if there's anything else, please let me know. And I think with that, we will be done with this talk.
Thank you so much. I just like to thank you all for listening and engaging with me. I feel very excited about this topic, and I see bright future that India can play a significant role, either in searching for the signal in radio waves or like launching this mission to the moon. So all of you are actually carry a huge burden on your shoulder to carry this forward. And I hope you actually contribute to this area as well. So all the best.
Right. So there's one question. I think we are
Yes,
trying to build a radio telescope. So if you can maybe share a few points on that as well.
sure.
Um,
So I think building a radio telescope would be using like a dish TV antenna would be a great way to demonstrate like how radio waves can be captured and converted and can be visually looked through. Um, you can use this tool called software defined radio called SDR, which are pretty cheap. They are like $35. You can buy them off the shelf, and they come with their own local noise, and you need to buy a local noise, low noise amplifier. So these are the two things that you would essentially need, because the kind of signal that we're trying to detect, although with a dish TV antenna, because it's so small in size, you will not be kind of making like a huge, you will not be able to detect extremely weak kind of signal. What you would be able to do is look at either like the sun or look at Jupiter, depending upon the frequency. But you can also look at hydrogen. So our galaxy is full of hydrogen gas. So typically, all of these radio antennas, you can buy the LNA, which are operating at these frequencies. So you can look at hydrogen gas in our Milky Way. And there is a very interesting experiment you can do, is that you can find out that by looking at the hydrogen gas, you can look at the Doppler velocity of the hydrogen gas. And then you can figure out that what are the different hydrogen clouds located at a different part of the galaxy. And if you draw a map of it, then you can figure out that we are actually living inside a spiral galaxy. So this was the first time. Before radio telescope, we did not know, because light does not travel too far. Light gets easily absorbed by the gas in the Milky Way. But the radio waves can penetrate all that. So you can look at radio waves even from the other end of the galaxy. So you can in fact map how the hydrogen is distributed in our galaxy. And using that map, you can find out that we are living inside a spiral galaxy, which will be a huge thing to show. In fact, these are the things that people have done in college courses. So I think it's pretty straightforward and easy thing to do. So you can do that using a small dish antenna.
okay, so those would be the first steps, I believe, to that. Okay.
Yeah.
All right. Okay. So once again, thank you, Vishal. I will be in touch with you and thank you out. So if there are no more questions, we would end this session. And please get in touch with me if you have any other concerns or questions. All right. Okay. Thank you, Vishal, for your time.
Thank you so much. Bye-bye.
Yeah. Bye-bye.